Okay, so I'm going to begin with something I did last time because it was not completed. Then we'll take it from there. And we had a lot more questions last time, which is good. It's very helpful, so I know what may be bothering you. So don't hesitate to stop me. The new thing we did last time was, if I give you some wave function psi of x, and I ask you what happens if I measure energy, the recipe is the same as in momentum. You got to find functions called psi sub e of x, which are supposed to be states in which if the electron was there, it'll have a definite energy. Now, not worrying for a moment on how you get them, the recipe for what happens when you measure energy is that if you're given some arbitrary function psi, that's a state the particle is in, and you're asking, what happens if I measure energy? What will I get? The instruction is to write that function as a sum over these functions, each associated with a definite energy. And once you have done that, the probability that you will get a certain energy E is equal to the absolute value squared of that particular coefficient. Not different from psi sub p, same rule. And the rule for A sub E is also the same or similar. A sub B is the integral of complex conjugate of this function associated with definite energy times the function you're thinking about integrated over space. It's the same rule. So it can happen, problem can take many forms. Sometimes one can give you a function psi of x, then you take all these functions, do all these integrals, find all the coefficients, and you square them. Other times the coefficients may be given to you, you just ask, what's the odd for this energy or that energy? But now the question is, what are these functions psi e of x? Whereas functions of definite momentum are given once and for all by this formula, e to the ipx over h bar. I wish I could give you a function of definite energy and say, these are functions of definite energy. Maybe instead of p, there'll be some e on the top. Because the reason is that the functions of definite energy depend on what the energy is in classical mechanics. And in classical mechanics, the energy depends on the momentum and on the potential energy. That means on the position. Every problem has a different formula for E. If it's a harmonic oscillator, this will be 1/2 kx squared. If it's a particle moving up and down in gravity, it could be mgey. If it's two particles connected by a spring, it'll be something else. So in each problem, or electron in a hydrogen atom, is the Coulomb force, Coulomb potential, E1, E2 over r squared times some 4 pi's. So in each problem, there's a different V, and for each V, you got to find the E. I mean, you got to find the functions. And what is the rule? The rule is the following. You have to solve the following equation, called the Schrodinger equation, d2 psi over dx squared plus Vx psi x equals E times. We just have to solve this equation. So let's not worry about how you solve it. That's a problem in mathematics. But the point is that given a potential V, you come to this equation, and you go to the math department and say, give me all the solutions of this equation. And they'll give you all the solutions of the equation. They will find, in fact, only for certain special values of E does the equation have acceptable solutions. And for each one, they'll give you the solution, and you start with that solution and do all of this. You follow that? That's the program. So I did a very simple example last time, which was two examples. First, I said, take the problem with no potential, no force. Particle is free of all forces. Then the equation is very simple. Minus h bar square over 2m d2 psi over dx squared. There is no v psi, that is just e psi. So let's rearrange this to the following form. d2 psi over dx squared plus k squared psi equal to 0, where k squared is just 2 me over h bar square. I've just, if you multiply by 2m over h bar square, you will get this equation. Since this combination appears all the time, I want to give it a name, k squared. But you must understand, okay, what's the relation of k to anything else you know will be clear in a minute. So what's the solution to this one? We can write them in terms of sines and cosines, but I want to write them in terms of exponentials, and the solution was, there are two solutions. One is e to the I kx, where k is defined that way. Other is e to the minus I kx. You can check if you took this function and take two derivatives of either this term or that term, both will give you minus k squared times the function itself. Because every time you take a derivative, you bring down an ik or a minus ik. But if you do it twice, it's minus k squared. And a and b are arbitrary right now. There is no restriction coming from that equation. And what is k? You know that functions of definite momentum look like e to the ipx over h bar, and I have something that says e to the ikx. It's very clear that p is just h bar k, or k is p over h bar. So if you like, this equation I got, we can write as h bar squared k squared is 2me. That means p squared is 2me. That means e equals p squared over 2m. So let's understand what that means. Yep?
Sorry, just jumping back for a second. At the bottom of the top board,
Yeah.
you wrote the E for classical mechanics.
Yeah.
And then did the equation to the right of that come from that?
In a way it does. That's correct. I will tell you how it does. But right now, I'm just giving you a recipe. Okay. If in classical mechanics, you know what the kinetic and potential energy of the particle are, kinetic is always p squared over 2m, potential is v of x, where v depends on the context, then in the quantum theory, the functions of definite energy obey an equation which looks a lot like that in many ways, right? So I've given you some clues or some more discussion in my notes on what is the universal recipe for guessing the equation in every context. I'll talk about it a little bit. But right now, you can take the view that this guy just tells me that if you want states of definite energy, solve that equation. Look, so what is this saying? Think about this. It's saying if you want a state of definite energy, it is really made up of states of definite momentum. And the momenta that appear here are not arbitrary. They are simply the momenta that you will have even in classical mechanics for that definite energy. Because if E is p squared over 2m, p would be plus or minus square root of 2me. That's exactly what we have. If k is equal to here, this says k is equal to square root of 2me over h bar, and h bar k is just square root of 2me. So that looks like classical mechanics, right? Even before you took the course, if I said that's a particle on a ring, its energy is E. What is its momentum? You will say, since energy is p squared over 2m, p must be plus or minus square root of 2me, and they mean going one way and going the other way. These are the only two options. That part is very much like classical mechanics. The k is related to E exactly the way it would be. What is novel here is that this state simultaneously can yield either the clockwise momentum or the counterclockwise momentum. That's the sense in which it's a different thing. You understand? A classical particle of energy E will have one of these two momenta, but on any given day, on any given trial, it will have only one of these two. It cannot have both the signs. Either it's going like this or going like that. In quantum theory, it's in the state of limbo. Not this alone, not that alone, both. The probability of going clockwise is proportional to a squared. And the probability of going counterclockwise is proportional to b squared. Right? I mean, if you want, you can put the square root of L's and so on, but they're all common to everything. So the relative probability is just in the ratio of a squared is to b squared. It's an admixture. And there is no restriction on how much of A and how much of B you should put into your answer. You can pick the extreme case where only A is non-zero. That's fine. That's a particle who has a definite energy and a definite momentum. You can pick this one, definite energy and the opposite momentum, but in general, both can be non-zero. It's a state of definite energy whose momentum is known in magnitude but not in sign, because both allowed signs appear here. The other result from quantum mechanics, which is surprising, is whereas a particle on a ring can have any momentum, in quantum theory, the demand that when you go around the ring, if you add an L to the x, you should come back to the same function, makes the requirement that KL is some multiple of 2 pi. That means K is equal to 2 pi n over L, or P is 2 pi h bar over L times n. So the allowed values of K or P are restricted in this way. The allowed values of energy then, which is P squared over 2m, are restricted to be 4 pi square h bar square over 2m L squared times an integer n square. And this is a problem where energy is quantized. It's really quantized because momentum is quantized. And the energy in this simple example is simply P squared over 2m. That means if you shine light on this system, it'll absorb light only at certain frequencies, and it'll emit light only at certain frequencies. And what are those frequencies? Well, all of this has a bunch of numbers. H bar, ml, they're not changing. N can be 0, plus or minus 1, plus or minus 2, etc. For every n you put in, you will get this basic number times 0 square or 1 square or 2 square. So you will find that'll be the state E0, which is n equal to 0. Then above that, that'll have an energy. Energy of that will be what? 2 pi square h bar square over ml square. Then there'll be n equal to 1, and there'll be n equal to minus 1. Both will have the same energy because energy depends only on n square. The energy of that will be, I'm sorry, I made a mistake. E0 is simply 0 because that corresponds to n equal to 0. E1 will be what I wrote here with n equal to 1, which will be 2 pi square h bar square over ml square. So what I'm saying is, at a given energy, you can have a state of right moving clockwise or anti-clockwise momentum, or a crazy mixture of the two. But normally, if you wish, you may select from these mixtures two special cases, one which is all A and one which is all B. We like those because now we can visualize them as states having a definite momentum clockwise, definite momentum counterclockwise. And that's what one really means by drawing two lines of that energy. So if you absorb a photon, you've got to give an energy equal to the difference of these two numbers, which is that. And that will be the h bar omega of your photon. And if you emit a photon and come from there down here, that photon frequency will be given by that. So this is how a quantum system is usually probed. We cannot actually look in and see anything. We deal with it by shining light. And we see what light it absorbs, what light it emits. The frequency of light is a clue as to energy level differences. You understand? Not to the energy themselves, but the energy level difference that turns into photon energy. But you can put together the levels by putting together all the differences. So you measure all the differences. So one famous line is the hydrogen 21 centimeter line. Hydrogen atom has two levels, which are very close, and the wavelength of that is 21 centimeters. It's a standard fingerprint of hydrogen anywhere in the universe. And sometimes, if the wavelength is not 21, but 22, we can say, why is it 22? The wavelength is longer. Maybe it's not hydrogen. Maybe it's somebody else. But the answer is that it is hydrogen, but that galaxy is moving away from you. So that its light is Doppler shifted into the red. And if something was coming towards you, it would be blue shifted. So you can tell, if you believe that hydrogen atom all over the universe are the same motion of the. And secondly, what's the speed of the galaxy. So the redshift is what one uses to find the whole story about galaxies. Yes?
In the context of a photon, or I mean, like an atom being excited by a photon, what does the L correspond to?
What is L for an atom, right? That's your question. Now, this is a fake atom. This fake atom is an electron moving on a ring, correct? That L is actually the size of that ring. You can go to a lab and you can make a ring of certain micron. Then the mass of the electron is known. That L will be the length of the ring. For an atom, what you have to do is that you must solve this equation where V of x is equal to what? In 3 dimensions, it will be the charge of the nucleus, which is Z times the charge of the electron, and is attractive 4 pi epsilon 0 r, which is the separation between them. So you'll have to solve a similar equation, but that equation will have d by dx and d by dy and d by dz and so on, right? It's in 3 dimensions, but this v of r will determine the allowed functions in that problem. That won't be an L, but a certain size will emerge even from that problem. That size will be the size of the orbit. For example, if you look at the function, the lowest energy state will look like e to the minus r over a0 times some number, where a0 is called the Bohr radius. That will be roughly 10 to the minus 8 centimeters. That a0 will be a length. You can say, where is the length and the height of an atom, right? It's no box. The length is the length made out of E, h bar, m. Okay, you can make a length out of those things, and that's what will come out. So if you want, you can take any textbook that gives you the formula for hydrogen's Bohr radius, that's supposedly the radius of the orbit, and you will find it's a length a0 made out of the parameters in the problem, which is the charge of the nucleus, charge of the electron, the mass of the electron. Okay. So this is, if you want, quantization of energy. Yep.
When you know the potential is 0, is it possible to measure both momentum and position, in that if you measure the energy and the position, don't you know something about momentum?
No, but you cannot measure energy and position at the same time either.
Okay.
Because energy, what you can really measure at the same time is energy and momentum. Because if you can measure P, you can measure P squared or P cubed, or any function of P. Because knowing a state of well-defined momentum in this problem doesn't do anything to the energy, because once you know that momentum is P, P squared over 2m is the energy. So it turns out this is a fortunate case where the two variables, energy and momentum, are simply related to each other in the fact that one is essentially the square of the other. But if you have two variables, one involving x and p at the same time, then you cannot measure that simultaneously with either x or with p. Yes?
What is A naught again?
Pardon me?
What is
A naught. Gee, I don't know. Bohr radius, I think it's h bar square over me square, but you have to check. I don't guarantee that answer, but I think it's something like that. You can see if it's got at least units of length. Yeah, I'm too lazy to try that. I think it's something like this. Anyway, suppose it is something like this. My main point is it is a length made out of Planck's constant, the mass of the electron, and the electric charge. Together they make a length. And that's the length that controls the size of the orbit. All right, so this was the simpler problem. Now I want to take a more complicated problem of what I call a particle in a box. So that's the potential. See, normally, if you make a hole in the ground, it may take this shape, and this is the location, and this is the height. But the height is just the potential energy directly, because it's mg times the height. So imagine a particle somewhere here. In classical mechanics, by the way, the rule for doing quantum mechanics is, in classical theory, what's the potential experienced by the particle? That's what you ask. And it is that potential that enters this crazy Schrödinger equation. So you need to know classical mechanics before you can do quantum mechanics. You should know what potential the particle experiences in classical theory and stick that into this equation to find the allowed energies in quantum theory. So if it's a vibrating system, there is some omega for vibrations. That omega is root of k over m, and you can get k from that one. Or if it's a system like an atom where there's an electric charge between them, electric force between them, you should know the electric potential. So you should know the potential in classical mechanics, and then you do the quantum theory from there. So imagine a particle in this potential in classical theory, and you ask yourself, what does it do in quantum theory? Well, classical theory says, let's plot the energy of the particle, right? It's some number that's not supposed to change as the particle moves. That means here, if the energy is kinetic plus potential, here the potential is 0, it's all kinetic. But as you start going near the edge, there are two parts here. That's the potential, that's the kinetic. And right here, all the energy is potential, and E is equal to potential. There is no K. What does that mean? That means the particle comes here, slows down, comes to a rest, then goes back. It can never be found here if it had this energy, because it's got more, it's got more potential energy than total energy. That means it's got negative kinetic energy. That's not possible. So every classical particle will execute bounded oscillations at any energy by between what are called the turning points. The left turning point, the right turning point is as far as you can go at that energy. If you've got more energy, of course, you can go further out. And if you've got even more energy, you can just roll up to the top of the hill and escape. That's classical mechanics. Now we want to ask ourselves, in quantum mechanics, what does the particle do? That's our goal. So I'm going to take a following simpler problem because it's mathematically easier. I'm going to take a potential that looks like this. It is V0 to the right of L, is V0 to the left of the origin, and it is 0 here. It has got very sharp walls because that makes it easy to solve the equation. In real life, potentials are rounded off. My fake potential has got sharp corners. And I want to take a particle of some energy and ask, what are the allowed energies in this problem? And what do the corresponding functions look like? That's what we're asking. So the rule is to go back to that equation, which now takes the following form, d2 psi over dx squared. I'm going to stop writing the subscript E. From now on, you should understand I'm trying to find states of definite energy E. 2m times E minus V psi equal to 0. I've just rearranged the Schrodinger equation so that it looks like second derivative plus all kinds of stuff. So how do we solve this problem? Well, V varies with position. So there are three regions in the problem. There's region 1, inside the well. Inside this well, V is 0. Outside this well, in region 2, it's equal to V naught, some constant. Likewise, in region 3, to the right of the well, it's also V naught. So we're going to solve this equation in three different regions: middle, left, and right. Okay, first let's solve it in the middle because it's very easy. So what is the middle defined as? Middle, region 1, V is equal to 0. So the equation is d2 psi over dx squared plus 2m E over h bar squared is 0. So let me write it as d2 psi over dx squared plus k squared psi equal to 0, just like before. This k is the same as before. K is equal to square root of 2m E over h bar. In region 1. So what's the answer to that one? Again, it's exponentials, but I'm purposely going to write it in region 1 as follows. as A cosine kx plus B sine kx. I hope you all know that besides exponentials, our old friends, the trigonometric functions, are also solution to this equation. Because the second derivative of cosine is roughly minus the cosine. Second derivative of sine will also give you minus k squared times the sine. So rather than using exponentials, I'm going to use sine and cosine because I have an ultimate motive. You realize that exponentials and sines and cosines are all connected by Euler's great formula. So if I want, I can take e to the ikx and write it as cos plus I sine, e to the minus ikx, write that as cos minus I sine, combine the cosines and call the coefficient A, combine the coefficient for sine and call it B, and get this form. There are two alternative ways. You just write this, you will see why I picked that. That's the answer in region 1. We are all set. Right now, A is arbitrary, B is arbitrary, and K is arbitrary. There is no restriction at all on any of them. Do you understand that? Because if you take this function, it satisfies that equation absolutely. So the free parameters are A, B, and K are all arbitrary. That means it can have any K. But the energy is h bar squared K squared over 2m, so it can have any energy. But we're not done yet because we only looked at region 1. I have to look at region 2 and at region 3, then you will find out what happens. So let's go to region 2. So in region 2, the equation obeyed by the psi, let me call it region 2 over dx squared equals minus 2m over h bar squared times v 0 minus e psi. I just put it on the other side now. Now this is all a constant. That's why we picked the potential, which is piecewise constant. So it's some constant. And you're asking yourself, what psi has the property that when I take two derivatives, it looks like this number times psi. So let me call this whole combination kappa squared. Then the answer is psi sub 2 is equal to c times e to the kappa x plus d times e to the minus kappa x. Why? Because two derivatives of this guy will give me kappa squared times itself, likewise here. And kappa has been cooked up so that kappa squared is what I want. Yes, now so kappa is equal to 2m over h bar squared times v0 minus e under root. So these are now real exponentials and not imaginary exponentials. The reason that used to be sines and cosines or imaginary exponential is that inside the well, e minus v is a positive number. Outside the well, I'm assuming that e minus v is a negative number. In other words, I'm going to consider the well to be, in the end, infinitely deep. And the energy of the particle, whatever it is some finite number. Because I want to send the walls to infinity. That's called particle in a box. So I'm taking v naught finite, but very, very large. Then it's very clear that v naught minus e is a positive number. This kappa is what I have here. Now look at these two functions. This function grows exponentially as you go to the right, to plus infinity. That means the wave function describes a particle that would rather be at infinity than anywhere near this well. So it's not the problem we are describing where the particle we expect is somewhere near the well. Furthermore, the square of psi can never be normalized to 1 because an exponentially growing function, the area under that is exponentially large. There's no way to fix that. So we, on physical grounds, we drop the solution because we don't have to pick c to be non-zero. We have the freedom, and the physical condition tells you no one wants a function growing at infinity. We want functions falling at infinity. This is the only function that falls at infinity. And how does it fall at infinity? How does it fall off? it looks like e to the minus square root of 2m over h bar squared times v0x. I'm ignoring e compared to this very large v0. Okay, I'm taking v0 much, much bigger than any energy I'm looking at. So it's falling exponentially, and the number on top is like square root of v0. So what do you think happens if v0 becomes very, very large? Well, if you plot the function that's exponentially falling, it falls like that. But as you increase v0, it falls more and more quickly. You follow that? And eventually, when v0 goes to infinity, it just doesn't have a life outside, just vanishes immediately. Whatever you start with goes to 0 immediately. That basically means psi 2 of x is just 0 in region 3. Region 3 if v0 goes to infinity. So let me emphasize what we are doing here. We have a particle in some kind of well, which is very, very tall, not yet infinite, and you give it some energy E, which cannot change. In this region, in classical mechanics, that would be the entire kinetic energy because potential energy is 0. What about here? This is the total energy available to you. Potential energy is all of that, so kinetic energy has to be minus some number. That can never be. That means that particle will never be found in the region outside this well. You understand? As long as the energy is less than the energy it takes to go to the top of the barrier and climb out, a classical particle, imagine rounding it off. You can come rolling with any energy. If you don't have enough energy to go over the top, you cannot be found in this region. But in quantum theory, as long as the well is not infinitely large, that's a small, exponentially small decaying wave function. So a classical particle will turn around at the classical turning points. A quantum particle will go slightly outside the forbidden region, into the forbidden region in both directions of the well. That is a purely quantum phenomenon. It is forbidden, meaning it's discouraged from going there, but it's not absolutely forbidden. Okay? That's called going over the, well, it's going into the classical forbidden region. But as the barrier gets higher and higher, the excursion into the forbidden region becomes less and less because the function falls very rapidly. And I'm considering, for simplicity, a barrier which is infinitely tall, in which case it doesn't go there at all, even in quantum theory. Therefore, by a similar argument, psi is 0 here and psi is 0 here. And in region 1, I've shown you psi is equal to A cosine kx plus B sine kx, where the energy is related to k by h bar squared k squared over 2m. So first, when we did only region 1, we get the impression that A and B and k can be whatever you like. But now we have an extra restriction. The restriction is that if you draw the function in this well, it can do whatever it wants, but it must vanish at the two ends. Because it's 0 here and it is 0 here. Just by continuity of psi, every psi that's allowed must vanish at the two ends. That's the new restriction. Because the function that I have here in general will not vanish at the two ends. But I'm going to demand that it vanish. That'll tell me something about the allowed values of A, B, and K. We'll see what it is. First, I demand that psi should vanish on the left edge of the wall, which is the wall at x equal to 0. This is the wall at x equal to L. Psi of 0 should be 0. I take the function I have. When this is 0, x is 0, that guy is gone. I get A times cosine 0, which is just A. But that has to vanish. That means the coefficient A has to vanish. It is not allowed. So even though it looked like, before we went to the other regions, you can have any A and any B. If you're only in the middle region, that's correct. But if you want to connect your answer in the middle region to a 0 on either side, then the coefficient have to be such that the side that you have in the middle vanishes at the left end. So A is gone. So I'm now left with only the following thing. Psi of x is equal to b sine kx. We did not have to kill b because at x equal to 0, the sign vanished. So it was allowed. But now I demand furthermore it should vanish at x equal to L. Well, at x equal to L, what do I find? I want 0 to be equal to b sine kl. That should be 0. Now, one simple way to get that is to kill b. Say b equal to 0. But then you got no solution. You killed a and you killed b. Certainly true that psi equal to 0 is a solution to this equation, but it doesn't describe anything. So you don't want to kill b, so you want to blame the 0 on the sign, and the sign, as you know, vanishes for any multiple of pi. You can have 0 times pi, 2 pi, 3 pi, 4 pi, minus 6 pi. They all give you 0 for sign. Therefore, k is quantized to be one of these numbers. Therefore, k has got only values n pi over L. I'm going to call it k sub n. And the energy, which is really h bar square k square over 2m L square, sorry, k square over 2m becomes now h bar square pi square over 2m L square times n square. And psi looks like b, psi sub n looks like b sine, let's see, n pi x over L. You guys see that? These are the allowed functions. The sine function is very nice. It vanishes on the left end because when x is 0, it's gone. When x is equal to L, the argument of the sine is a multiple of pi. It vanishes, so it looks like this when n is equal to 1. It looks like that when n is equal to 2, and so on. So it's got more and more wiggles in the region in between, but they are designed so that they vanish precisely at the edges. So it's exactly the case of a violin string that's clamped at two ends, which has to vanish at the two ends because you don't let it move there. In between, it can do this and it can do that. It can have more and more wiggles. So what you find is, of the three things that we thought are arbitrary, A is gone, and K is not arbitrary. K is again quantized to be what? N pi over L, so that the function does n half oscillations between one end and the other end. And therefore, there's a corresponding quantization of energy. Yes?
Now, what does that tell you? If you square psi n, does that give you the probability of finding it in each one of the energy levels?
No. Let's talk about that now. So let's write down the function. The size of energy that we were looking for, we have finally found out. So let's have a picture in our mind. Here is the well. It's going all the way to infinity. There is a state n equal to 1. And the function looks like, function looks like this. Then there is a state, let me draw it right there. It looks like that, n equal to 2, and so on. In the psi sub n, let me label the energy by n, is equal to some constant b times sine n pi x over L. That means if you want a particle in the well to have a definite energy, the wave function must look like one of these sine functions. It must look like this, or it must look like that, or the higher harmonics. They are the only allowed functions for states of definite energy. Now, before I answer any further questions, the allowed values of n here, you might think are 0, plus or minus 1, plus or minus 2, etc. But I claim they're just 1, 2, 3, and so on. You should think about why. What's wrong with n equal to 0? that a possible value? Can anybody tell me what happens to this function if, yep? If n equal to 0, the function identically vanishes, right? Because sine of 0 times pi x over L is identically. That's not what you want. You want a non-trivial solution. So we drop this guy. But how about n equal to minus 1? Why don't I keep that? Yep. Oh, I thought I imagined a hand going up. Yes?
It is the same thing as negative b sine of the positive n.
That's correct. If you put n equal to minus 1, the function psi of minus 1 is b sine minus pi x over L, but that is equal to minus 1 times b sine pi x over L. This guy is just psi 1. So it is just a multiple of the psi 1 function, because minus 1 times the state is the same state. You don't get a new function, you just get a multiple of the old function. And in quantum mechanics, they're all the same. But be very careful. When I did a particle on a ring, I did e to the IP x over h bar, where I said p is equal to 2 pi h bar over L times any integer n. There I let n be equal to 0, plus minus 1, plus minus 2, etc. Why did I allow that? First of all, in that case, e to the I times 0 is not 0. It's in fact constant. So for a particle going in a ring, the 0 momentum state is actually allowed. And plus 1 and minus 1 are not the same, because e to the IPx and e to the minus IP, I forget the h bar, they are not proportional to each other. You understand that? You can never write e to the IPx as a multiple of e to the minus IPx. You see that? If there were such a multiple, let me call the multiple as n, then n is really e to the 2 IPx by bringing it the other side. That's certainly not a constant. So e to the IPx can never be converted to e to the minus IPx by multiplying by any number, so it's an independent solution. On the other hand, sine x and sine minus x are related to each other by a single factor of minus 1. So that's the reason why, in that case of a particle going in a ring, the solutions are labeled by all integers, positive, negative, and 0. For a particle in a box, they're labeled only by positive integers. Negative integers give you the same function, and 0 kills the function, so that's not allowed. Okay, so what about B? What shall I do with B? What equation is going to determine B? Yes? Any idea? Yep.
We want psi to be normalized, right?
Right. So first of all, the equation will never tell you what B is. That's what I want you to understand. The equation that I've written here for the energy functions on the top, if psi sub B is a solution, you can multiply both sides by any number, like 15. Then 15 times psi will also be a solution. That's a property of a linear equation, that the answer is not given in overall scale. Give me one answer, I rescale it, it's still an answer. So a linear equation will never tell me the overall size of the function. That is picked by the extra convenient restriction that psi square dx be equal to 1. That will determine B, and I'm claiming the answer is its square root of 2 over L is what you want B to be. The answer is again simple. The average value of sine square over a half period is 1/2. If you square and integrate over L, you will get L over 2. So B squared times L over 2 should be 1, and B should be therefore root of 2 over L. So let me write down now the final result of this problem, which I think is very, very instructive. If you can follow this much, you really got 80% of the quantum mechanics I want to teach you, if you're comfortable with this example. Because we are trying to find out, in quantum theory, you got a particle in a box, which is like a hole in the floor, which is so deep that it's infinitely deep. But even if it's not infinite, but very deep, the answer is good enough. You want to know what it will do. In classical mechanics, what will it do? If you're a particle in a box, what's your lowest energy state? Yes?
Floor of the box.
If you're in a prison with infinitely tall walls, you just sit on the floor and mope, right? That's the lowest energy state. But that's not allowed in quantum mechanics because you have a definite x, which is wherever you're sitting, definite p, you're not moving. Such a state is not allowed. So in quantum mechanics, a particle cannot simply sit still. Therefore, it will necessarily have an uncertainty in position. And it will try to spread itself over the box. And the typical uncertainty is of order. If I say, where is this particle? I don't know anything. It's got to be somewhere in the box. That's the estimate for delta x. So delta p is got to be big place. So it cannot have zero momentum. Its momentum has to be fluctuating with that range. And the kinetic energy, which is in fact the total energy inside the box, which is p squared over 2m, the size of that is h bar squared over 2m L squared. So that is your estimate for what should be the energy of a particle in a box of size L. So what happens is the box of size L forces it to have a spread in momentum because you squeezed it to position known to within L. The spread in momentum translates into spread in kinetic energy. And if you take the spread in kinetic energy to be a rough estimate of the lowest kinetic energy I could have, you get a number which, except for factors of pi, is in fact the right answer. So people always estimate energies of particles by doing this calculation. For example, take a nucleus, which is 10 to the minus 13 centimeters across. I put a proton there. What's the minimum kinetic energy of that proton? You find by the following method. Delta x is 10 to the minus 13 because it's somewhere in the nucleus. Delta p is that, and you do that, you'll get some energy. That'll be the typical energy of a particle inside the nucleus. So particles inside the nucleus cannot sit still. More you cram them, it's like children. You put them in a tighter room, they're jiggling more and more. Okay? That's called zero-point motion. You just cannot nail them in x without letting them spread in p. That means you cannot get lowest energy. So the lowest energy is some number you can estimate by the uncertainty principle. So the next question was, let's take one of these functions, say psi sub 3. The square root of 2 over L sine 3 pi x over L. If you plot that guy, that function will look like this. Now, what was your question? If I measure the particle's position, what's the probability? You just got to square this function, which will look like this. That's the probability. If you measure the energy, what will you get? You will get exactly one energy corresponding to n equal to 3. It's in a state of definite energy, but not definite position. Position has got some ups and downs. The probability for x looks like that. So everyone with me? This is like knowing the spectrum of this artificial atom. In a real atom, the electron is forced to stay near the nucleus because the 1 over r potential, if you plot it as a function of r, looks like a well. And the particle is somewhere here. In this problem, the particle is confined by the box. Whenever you have a confining thing that keeps the particle in a certain region, the energy gets quantized. And we have found out in our first example the quantized energy levels of a particle in a box. And you can probe the particle by shining light, and the energy levels are plotted like this. This is n equal to 1. This is n equal to 2, which is n equal to 3. 0 is here. The 0 state is not allowed. You've got to have n equal to 1, and 4 times that will be n equal to 2, and 9 times that will be n equal to 3. Energy grows like n squared. And then you can come from there to there emitting a photon, or you can go from there to there emitting a photon. You can go from here to here absorbing a photon. You can do all kinds of things. That's how, if you want, you can test quantum mechanics. Put a known particle inside the well and shine light and see what light it absorbs. Yep.
So psi sub 3, is that the psi for the energy group?
Yes. Exactly right. So what I should really write, he is absolutely right. I should write E equal to h bar square pi square over 2m L square 3 square, right? The third energy level. So I'm short-circuiting all of that and just calling it psi sub 3. Normally, if you put a label 3, it's not clear what we're talking about. Maybe it's the position x equal to 3. Maybe it's the momentum p equal to 3. But in this lecture, since we're talking only about energy, I thought I will just call it psi sub 3, but at least I should call it psi sub E3.
And then so you said you can square that function and give you the probability of where the position.
Yeah, I just did that.
But I'm confused why you don't need to take the integral with the complex conjugate.
You can take the complex conjugate, but for a real function, you can just square it, right? You understand? If psi is real, psi star is the same as psi. So psi star is also 2 over L sine 3 pi x over L. So psi is just a square.
On the first floor at the top, you have a sub e equals the integral of psi star e times psi of x.
Yeah?
And so I'm wondering why there's no like n one. Why we're not doing like.
No, I think I know what the problem is you're having now. That formula is not relevant now. I'll tell you when that formula will come into play. Okay? It'll come into play in the following situation. I have a particle in a box whose wave function looks like this. Somebody put it in that state. It's an allowed wave function because it vanishes at the ends like it should. Beyond that, it does anything it wants. That is my psi of x, okay? If I measure the energy of that guy, now you tell me, if I measure the energy in that state, what answer will I get? Pardon me? Yes, I'll get one of those quantized values. You understand? A particle in a box under energy measurement can give only one of those numbers. Now, this guy is not one of those functions. You understand? This is a randomly chosen function. But when I measure energy, so what will I do? Maybe you can guess now. That's correct. You will have to write this guy as a sum of a, let me call it n for energy now, a square root of 2 over L sine n pi x over L. I mean, this is just a sub e psi sub e of x, except e is labeled by an integer, so I'm writing it this way. Then I have to find a sub n. And if I want to find a sub n, that's equal to integral of 2 over L sine n pi x over L. If you want, you can put a conjugate, but it doesn't matter because sine is real. Multiply it by Mr. Crazy here, okay, whatever it is, and do that integral. It'll give you some number for every n, a1, a2, a3, a4, and the square of every one of them will give you the odds that you will find this energy or that energy or some other energy. So what quantum mechanics tells you is an energy measurement of a particle in a box cannot give a random answer. It can only give one of these answers. That's the quantization of energy. It does not mean every particle in a box is in a state of definite energy. A particle in a box can be in any wave function provided it vanishes at the ends and doesn't spill out for the infinitely tall wall. So for every one of them, you can ask the usual questions. What happens when I measure position? Square the function. What happens when I measure momentum? Write it in terms of e to the ipx functions. What happens when I measure energy? Write it in terms of these functions. Okay? All right, so I want to do one last topic here, which is called scattering, but I don't want to proceed till you guys have understood this part. This is covered in all the books. Maybe you can read the books or you can read my notes. You can talk to everybody. What we have solved from this, all quantum problems that we all do are exactly isomorphic to this problem. It's the same thing we do over and over again. Except the equations you solve are more difficult. They can be in higher dimensions. They can involve more than one particle. The potential could be complicated, but the philosophy is always the same. There'll be some Schrodinger equation, and you want to find all the functions that satisfy it. Find the allowed energies and the allowed functions. We will see that states of definite energy have a very privileged role in quantum mechanics. That'll be clear in the next two lectures. But right now, here's what I want to do. This is a very small variation of what we have done. So most of the hard work has been done. So I'm just going to cash in on that. Take the following problem in classical mechanics. Here is the level ground. Then I make a little change in the landscape so that this has got certain height and therefore certain potential, V naught. And from this end, I roll a marble and see what happens. The marble is given some energy E, which, because there is no potential here, is just p squared over 2m. Question is, what will happen? Can you tell me what will happen in this problem to this marble?
Well, don't we have to use the Schrodinger equation?
No, classical mechanics.
Oh, the marble will only go up as far as it has the amount of energy that would equal the potential energy.
That is correct.
At that point.
That's correct. So he said it'll go as far as energy equals potential. So let p squared over 2m have this value. That's my energy. And it does not change. That's the law of conservation of energy. So here, since energy is kinetic plus potential, it's all kinetic. Somewhere here, that part of it is potential, rest of it is kinetic. Here, kinetic vanishes. Here, you're not allowed. So you will go, you'll climb that far, and you'll come back. But if your initial energy was that, then you will come here, going very fast, you will slow down, but you still make it on the other side, but with lower velocity. That's very simple. That's only one answer you can get. You throw something. If it comes back, it means the barrier is taller than what you have. Suppose you cannot see this barrier. All you have is a marble, and you want to know how tall the barrier is. Very easy. Throw the marble at a known speed. If it comes back, then you haven't reached the top of the barrier. Keep on increasing the kinetic energy till one day it doesn't come back. But that's when you're sitting right here. That's one way to tell how tall this hill is without actually going there. But now what I want to do is to do a quantum mechanical experiment in exactly the same situation. I want to send a particle from the left, and I want to see what happens. So now, to simplify the problem, I'm going to take the potential to, again, have only two values. At x equal to 0, it jumps to a value V naught. So this problem is just the Schrodinger equation in the left region, Schrodinger equation in the right region. So I'm going to spare you some of the calculation because it's so familiar. One will look like A e to the ikx plus b e to the minus ikx, where k square is just 2me over h bar square here. First, let's take a case where E is bigger than V naught, okay? Then I go to region 2. Region 2, I got to solve a Schrodinger equation with a V naught in it. Then you will find in region 2, psi 2 looks like C e to the ik prime x plus d e to the minus ik prime x, where k prime square will be 2m times E minus V naught over h bar square. Because when you have a potential, you must always have, look at the Schrodinger equation here, 2m over h bar square times E minus V. So V is not 0. The k prime now, so what does this mean? You can see very simply, it's got some momentum here. It's got a smaller momentum here because k prime squared is going to be smaller than k squared because V naught is non-zero here. That is just a statement that when the particle is moving here, it's slower than when it's here because it has to climb up the hill. So the wave functions in this region has got an incoming right-moving wave of momentum h bar k. It's got a reflected wave of momentum minus h bar k. And in this region, again, it's got a right-moving and a left-moving because this k can be of either sign. So you can pick the coefficients a, b, c, d arbitrarily, but I'm going to choose d equal to 0 Because what I have in mind is a problem where the particle actually came in from the left. If it came in from the left, I'm prepared for some of it coming back, reflected, and some of it getting transmitted. There's nobody coming in from the right at plus infinity because I'm not sending anything from there. I'm sending my particle from the left. So I pick a solution in which d, which is anything, I pick that to be 0. So here is my two solutions. I hope you understand that k and k prime are not the same number. K prime is smaller because the momentum on the right-hand side is going to be less because some of it's eaten up by potential energy. So what people do is they draw a picture like this. They draw a wave that's going at some speed, and it comes in this region, and it slows down. That's what the function will look like. The real function is made of exponentials, but the real imaginary parts will have rapid oscillations on the left and slow oscillations on the right because k is bigger than k prime. Very good. So now I have the following condition. At the interface where the two regions meet, the psi must match from the left and from the right. So at x equal to 0, coming from the left, I want psi 1 at 0 should be the same as psi 2 at 0. That will tell me that a plus b equal to c. Because if you put k equal to 0, if you put x equal to 0, all the exponentials become 1, and a plus b must be equal to c. There's a condition that if you come from the two sides, the wave function has to match. But in the Schrodinger theory, you make a second requirement that the derivatives also match. The two functions coming from the left and right cannot join like this. They must join with the same slope. The reason the slope must be same is that if the slope change abruptly at one point, the rate of change of slope will be infinite there, because d2 psi over dx squared is the rate of change of the slope. But in the Schrodinger equation, the second derivative of psi, if it's infinite, there is no compensating terms in the equation because e and v are all finite. So that infinity will not be balanced, so you can never have that. So second derivative must be finite, first derivative must be continuous. So I make the requirement that d psi dx in region 1 at x equal to 0 must match d psi 2 dx at x equal to 0. What does that give me? Well, take the derivative and equate them at x equals 0. You will find ik times a minus b is equal to ik prime times c. Right? Take the derivative and then equate the derivatives at x equal to 0. Derivatives brings down ik for this, minus ik for that, blah, blah. You put them together. So these are the two conditions. Now, what causes mild panic is that I have three unknowns and two equations, because I got a, b, and c, and I got only two equations. So what do you think is going on? Anybody have an idea? It's that even in the particle in a box, you remember the overall height of the wave function is never determined by the Schrodinger equation. It's whatever you like. So what people do is they say, let's pick a equal to 1. That sets the overall height arbitrarily. Then I get 1 plus b equal to c, and ik times 1 minus b is equal to ik prime. Now, of course, you can solve for b and you can solve for c. And I'm not going to do that here. It's very easy. You're going to find b is equal to k minus k prime over k plus k prime. You're going to find c is equal to 2k over k plus k prime. That's simple algebra of simultaneous equations. But I want you to look at the answer. You remember now what a, b, and c are. A comes in, b goes back, and c goes to the right. What do you find strange about the answer? Is that if you came in from the left with an energy bigger than the barrier, there's a certain probability that you will go backwards In classical mechanics, if your energy is more than the barrier, you will never come back. Probability is 0. In quantum theory, even though your energy is more than the barrier, there's a certain probability to get reflected and a certain probability to get transmitted. The square of this is like the odds of going to the right. Square of this is like the odds of getting reflected. The point is the reflection probability does not vanish even if the energy is bigger than the barrier height. That's because this is quantum mechanics, and you're really dealing with waves and not particles. And waves have the property that when the medium changes, there is some reflection. And to the light wave, to the quantum mechanical wave psi, a barrier looks like a change in refractive index. So it'll get reflected and some will get transmitted. But the interesting thing is, in the quantum problem, you can send your billiard ball to find how tall the mountain is. And even if the energy was more than the mountain, sometimes it'll come back. So that's not a reliable way to measure that. The last example is, what if your energy is less than this? What if your energy is like here, lower than the barrier? If it's lower than the barrier, you will find that kappa, the k prime, will be equal to I times some kappa, because it will become imaginary, and you will have then a function that looks like this. The function will oscillate, then it will die exponentially in this region. It is exactly what I did earlier, like particle in a box. In the classically forbidden region, it goes a little distance, but not very far. So it does get reflected if the energy is less, but you can actually find it in a region where it's not supposed to be. And you can say, that's going to be very embarrassing for the particle to be found here, because its kinetic energy should be negative here. So what's the particle say to you when you catch it there? It'll say, in order to locate me here, you shine some light on me, and the energy I got from the photon made me legitimate in that region. So it'll come back to positive energy. So the act of measurement will prevent it from ever being caught in that region, but it's got an amplitude, a probability to be caught there. Final thing I want to mention is, if this barrier, instead of going on forever, terminated there and became 0 again, this will leak out here and start going out to the same wavelength as that one. That's called barrier penetration. That means if you send a particle here with an energy not enough to overcome the barrier in classical mechanics, in quantum mechanics, it's got a small chance of being found on the other side. On the other side, it can go scot-free. See, it's not allowed in this region, because there the kinetic energy is negative. Here, kinetic energy is the same as before, except the height may be very small. So this means no barrier is completely safe in quantum theory. So I'm going to give you my final survival tip. I've told you so many situations you can be in where this course will help you. So here is another one. You are in a prison, and it doesn't have infinite walls, but it got some walls. What's your strategy? I say go ram yourself into the wall as often as you can, because there's a small probability that you can suddenly find yourself on the other side. Okay. This is what happens in alpha decay. In alpha decay, there's a helium nuclei sitting inside a nucleus. There's a barrier that keeps it from coming out of the nucleus, but the barrier goes up and comes down. So if you go a certain distance from the nucleus, you're again free. So the alpha particle does exactly what I told you. It goes rattling back and forth inside the nucleus, and once in a while, it penetrates and comes to the other side. And that's the alpha decay of the nucleus. So this really happens. It may not happen to you in the situation I described, but the probability is not 0.